Today we're going to continue our exploration of generating series. In our first video, right over here, we actually took a look at how to use series, power series from calculus, to do counting for us. Now we're going to see how we can extend that to get interesting identities between two counting problems that at first don't seem like they count the same thing, but end up counting the same thing in the end. Hey, welcome to today's video. I'm Prof. Omar. This channel is dedicated to undergraduate theorems and problems for your experience through the undergraduate and to prepare you for your journey beyond. If that resonates with you and this is your first time on the channel, definitely subscribe and click the bell button for notifications on future videos. And if you are a subscriber, thanks for coming back. So today we're going to explore generating series and using them to establish identities between different counting problems that we don't necessarily see at face value actually count the same thing or are counted by the same numbers. Our exploration today is going to deal with what are called partitions of numbers. So let's define them right now. Okay, so a partition of a positive integer n, so we're given a positive integer, stapled, is an unordered sequence of positive integers whose sum is n. So let's break this down with an example to get a sense of what this actually means. So let's take, for example, the positive integer 5. So here is one way to express 5 as a sum of positive integers. We can write it as 3 plus 1 plus 1, right? And so the sequence 3, 1, 1 is an example of one particular partition of the number 5. And we usually write it with parentheses here. So there's an example of 1. Another one is maybe 2 plus 1. And these two partitions happen to have the same length. Another one is 2 plus 1 plus 1 plus 1. That has a few more elements than the previous partitions that we had before. Now, another way to write 5 as a sum of positive integers is 1 plus 2 plus 1. But that's actually the same as the partition right over here because we've demanded that the partition is an unordered sequence, right? So switching the order won't change the actual partition. So in that light, we usually write the partitions where the positive integers descend from left to right, because if we reorder this, we get the same partition. Okay, so let's actually see what all the partitions of the number 5 are. So it turns out there are 7 partitions of 5, and they're all right over here. We have 1 of length 1, 2 of length 2, 2 of length 3, and 1 of length 4, and 1 of length 5. Right, so 7 partitions in total. All right, so we usually have a notation for the number of partitions of a positive integer n, and that notation is p of n. Now, finding an explicit formula for p of n is actually kind of a challenging thing to do. There are asymptotic formulas and some formulas that come really close, but there's a lot of analytic tools that are required to actually get an explicit formula for p of n in terms of n. But we'll see that we can at least get some ideas using generating functions. And then we're going to see how to relate the number of partitions of a certain type to the number of partitions of a totally different type using generating functions. Okay, so when you look at any particular partition, it has a number of copies of positive integers. Like here we have 2 copies of 2 and 1 copy of 1. Here we have 5 copies of 1, right? And for example, if we had a partition of 7, or maybe I'll pick something larger like 17, we could have something like 3 plus 3 plus 3 plus 2 plus 2 plus 2 plus 2, right? So 3 copies of 3 and 4 copies of 2. So what we can do to find a generating function that encapsulates this statistic that we called p of n, which was the number of partitions of n, is we can develop a way to keep track of the number of copies of each of these positive integers. So we're going to keep series here that keep track of the number of 1s, the number of 2s, the number of 3s, the number of 4s, etc. Okay, so let's do that in each case. So again, one of the things that we did in the previous video on generating series is anytime we're doing some type of counting, we keep track of each of our constituents in the exponents of a series. So here we'll keep track of ones by saying, okay, we might have 0 ones, or we might have 1 1, or 2 ones, or 3 ones, etc. Okay, and the number of 2s, well, we might have 0 2s, we might have 1 2, which contributes 2 to the actual count that we're interested in, so we're going to record that with an exponent of 2, right? So we have 1 copy of 2, and then we might have 2 copies of 2, 3 copies of 2, etc. Okay, same thing with the 3s. A copy of 3, 2 copies of 3, 3 copies of 3, etc. And then the 4s. A copy of 4, 2 copies of 4, 3 copies of 4, etc. Okay, so imagine doing this infinitely. So for every single positive integer, we write down a series that keeps track of the number of possible constituents or summands that appear for that number in your particular partition. Okay, so what would happen if we actually multiplied all these infinite series together? Let's think about this in the same light as the video that we watched previously. So let's look, for example, at a prototypical element in the product of these series right over here. So maybe we'll have something like this term right over here multiplied by this term multiplied by this term, and then multiplied by all the x to the zeros afterward. So that term would look like x to the 2 times 1 times x to the 1 times 3 times x to the 3 times 4, right? Which is x to the 2 times 1 plus 1 times 3 plus 3 times 4. Now let's think about what this exponent is actually keeping track of, given what we said our exponents are keeping track of up here. So here we're saying that we are looking at a partition that has 2 1s, 1 3, and 3 4s. So it's a partition that looks something like this: 3 4s, 1 3, and 2 1s. So this is a partition of the sum of these, which is 12, 15, 17. All right. Now you notice that if you actually expand and find a product of monomials from one from each of these terms whose exponents sum to 17, it gives rise to another partition of 17. So by the same mantra in the previous video, if we were to collect the x to the 17th term in this entire product, whatever the coefficient is going to be the number of partitions of 17. And we actually see explicitly what's happening in the exponent every time we do a particular multiplication. Okay, interesting. So another thing we can observe is we have a compact way of writing each of these series. This goes on forever. Here we have the sum of these monomials, which by our previous video is 1 over 1 minus x. Here we have even exponents, x to the 0, x to the 2, x to the 4, x to the 6, etc. And so that'll work out to 1 over 1 minus x squared. Here we'll have the compact way of writing this as 1 over 1 minus x cubed, etc. So if we were to ask the question, what is the number of partitions of a given positive integer n, we could say that the number of partitions is the coefficient of x to the n in this infinite expansion of the product of an infinite number of power series. And it's this product 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x cubed, etc., going on to infinity. Now, there's a little bit of a problem with this, which you might see already, which is what does it mean to take an infinite product of power series? So I'm not going to think about radius of convergence issues right now because it turns out there's a way that you can completely bypass that using some algebra, but we don't really have the equipment to do that. So I'm going to say that there is algebra you can do that bypasses issues of convergence and still lets you do things like this. But here's the point. In terms of why you're okay saying that P of n is the coefficient of x to n in this infinite product. When you think about a particular value of n, like let's say 17, not many of these terms are actually going to contribute to the coefficient of x to the 17. Because when we get to say like the series associated with the number 18, we're going to have a series that looks like x to the 0 to start, and then x to the 18 as a second term, and x to the 36 as a third term, etc. And none of these will contribute to the x to the 17 coefficient because the powers are too high, except for this x0. So after starting with the 18th series onward, the only contribution to the x to the 17th term is the x to the 0 term in each. So none of those really play a role, and so we're okay to do something like this. Okay, you might also ask this question, what's the point of even talking about the number of partitions of n being the x to the n coefficient or something like this? It doesn't seem like it's of use practically. But now we're going to see that if we change things up and ask for partitions of certain types, we might actually be able to manipulate the series to get identities that we wouldn't have known in the first place necessarily. Okay, to motivate our exploration, what I want to do is look at the number of partitions of a positive integer n in which each part has to be an odd number. So for example, if we looked at the number 5, an example of such a partition would be 3, 1, 1. You notice every single part here is an odd number. Another example is 1, 1, 1, 1, 1. At first, this seems like a really random thing, but I'm going to give a sense in a little while of why this might be interesting. So let's develop a power series whose coefficient of x to the n tells us the answer to this. And that's sort of the goal with generating series, and then we'll manipulate this to figure out something actually quite interesting about this count. Okay, so again, the idea with the generating series is to look at contributions individually. We'll look at the number of ones in the series. Now, here each part is odd, so we don't have twos. So we'll have the number of threes, and then the number of fives, the number of sevens, and then look at series that dictate the contribution of each. Okay, so here we can have any number of ones that we want. So we'll have this series right here that keeps track of the number of ones in the exponent. For example, this term is saying we're picking 3 ones. And then we'll keep track of the number of threes in this series, 2 threes, 3 threes, etc. Here the number of fives. And here the number of sevens. Okay, and so the number of partitions of n with each part being odd is the coefficient of x to the n in the product of all of these series. To get a sense, let's actually look at where we can see this with the number 5. So 5 is x to the 5 times all these x to the zeros. And that contribution comes from selecting 1, 5 and no other terms. To look at where this partition comes in, we're picking 1, 3, so that's this 1, 3 right over here, and 2 1s, which is coming from this contribution right over here. The 5 1s would come from the x to the 5 term here, keeping track of the number of 1s. And then here we'd be multiplying these two by all of these x to the zeros afterward. Okay, so we can collapse this and say then that all of these series look like these individual series here, except we're getting rid of all of the ones with even exponents. So the number of partitions of n in which each part is odd is the product of every other one of these series that we have over here. So what I'm going to do is write that on the corner, and then I want to investigate it for a bit. So we've established that the number of partitions of n, each part of which is odd, is the coefficient of x to the n in this series right over here. So what I want to do is actually play around with this series and make this really spectacular observation about it. So I'll write the series out here. It's 1 over 1 minus x, 1 over 1 minus x cubed, 1 minus 1 over 1 minus x to the fifth, etc. And you notice you're removing all of the terms that look like 1 over 1 minus x to an even power here. So what I want to do is reintroduce those and see what happens. Now we can't exactly reintroduce those because they're not there. So if we try to reintroduce them, like a 1 over 1 minus x squared, we need to have a 1 over 1 minus x squared in the numerator. Okay, so let's do that here. We'll have 1 over 1 minus x cubed times 1 minus x to the fourth, 1 minus x to the fourth. And then 1 over 1 minus x to the fifth times 1 over 1 minus x to the sixth over 1 minus x to the sixth, etc. Now, if we do that, we get the product of all terms of the form 1 minus x to the something in the denominator. Okay, and then in the numerator, we get 1 minus x to the even ones. Now, each of these 1 minus x to the even exponents is a difference of squares, so we can actually factor each of them. So for example, this one is 1 plus x times 1 minus x. This one here is 1 plus x squared times 1 minus x squared. And here we have 1 plus x cubed times 1 minus x cubed. Now, since we're doing this infinitely, every single one of these terms in the numerator is going to have every single one of the terms in the denominator. For example, 1 minus x appears here. 1 minus x squared appears here. 1 minus x cubed appears here, etc. Like we'll have a 1 minus x to the fourth in the next term when we introduce 1 minus x to the eighth here. And so all of the denominators will actually clear with these factored versions of the numerators, and we'll be left with just these 1 plus x to the somethings. 1 plus x, 1 plus x squared, 1 plus x cubed, 1 plus x to the fourth, etc. So this is a completely different representation of this same series right over here. Okay, so you might think, okay, I have to be careful, there's infinite products here. I'm going to ignore that for now because, as I mentioned, there's a way to deal with that that uses an algebraic setting that we don't really have the tools to deal with. But we'll say that this series actually is the same as this series right over here. Okay, so what we're going to do is going to clear the work that we've done to get here and write this right below this and then analyze what this is counting. Okay, so we've established the equality of these two things by massaging the power series themselves. Let's look at what this thing is. If we think about each factor again as the number of contributions of a given positive integer towards a partition, let's analyze. This piece here would say something like the number of ones is either 0 or 1. And this next series would tell you that the number of 2's in your contribution is either 0 or 1 as well. You only have 1, 2 in your exponent. The next thing, the number of 3's is either 0 or 1, etc. So a way to interpret the product of all of these series is that the x to the nth coefficient is the number of ways to write n as, or the number of partitions of n where you only have exactly one copy at most of each one of these numbers. Another way to remember that is it's the number of partitions of n where every part is distinct. Okay, so if this thing is the generating series for the number of positive, or the number of partitions of a positive integer into parts that are distinct, and this is the number in which each part is odd, that means that the number of partitions of a number n in which each part is odd is the number of partitions of n in which each part is distinct. That's fascinating if you think about it. And the reason we were able to see this is because of massaging the generating series. And this is one of the things that you get with generating series is identities like this that you may not have seen otherwise. Let's actually check that that's true with an explicit number. So let's look at the number 7 to make things a little bit large. And let's look at partitions of 7 in which each part is odd and partitions in which each part is distinct. Okay, so here are the ways to write 7 as a sum of integers in which each part is odd. And here's a number of ways to do it where it's distinct. And we notice here we indeed have 5 ways to do each of these. So this is a really, really cool technique. And the thing that we like to do in combinatorics is to think, now that we have this power series revelation, our hope is to find a direct reason why this equality actually holds. So there is a really cool reason why this holds, and I'm going to actually let you try to figure out why. One hint that I'll give is one way to draw partitions is in a form called the Farrer's diagram, where you write rows for each part, and the number in each part you write as a sequence of dots. So for example, the Farrer's diagram for this partition right over here would have 3 dots for that first part, then 3 dots below for the second, then 1 on the bottom. With help from this diagram, you might be able to get an idea why these two are equal directly from the picture. Beforehand, right, we might not have made this observation, or it might not be clear to us why there is a direct relationship using a picture, but we can at least use generating functions to explore and figure out why. And this is a great example of that kind of phenomenon. So I hope you enjoyed today's video. If you did, click the like button. If you want to see more videos like this, subscribe to the channel and click the bell for notifications on future videos.